Good morning, everyone. Today is the second video for chapter 12, which is our last chapter, and hopefully we will finish it today. Um, we were discussing about regression and correlation, and we defined how we can find how we can find the equation of a line that is best fit for our estimation or for our our predictions. Like we have discussed last time that how we can find out the least square regression line. This is called least square regression line, which we were finding it out in terms of y equals to ax plus b. On your calculator, we have seen that when you use stat and go to calc and then go for linear regression, you can find the equation by using the list of values for dependent and independent variables. And then we found the correlation coefficient, which which tells us that what is that how these two variables are correlated to each other. And we were defining we were defining the Pearson correlation coefficient for the simple linear regression equation. So it is represented with R, and we have seen that how it could be a bad fit and good fit for the linear line. If our R value is greater or equal to 0.75, then it means it is good fit, or if it is less than or equal to minus 0.75, then it is also a good fit. The only reason we have negative and positive values for R, that for instance, if your X values are increasing and Y values are increasing in the scattered plot, then R is positive, like it has to be greater than 0. Or if your X values are increasing and your Y values are decreasing, then we can have another type of line for which we can use our, which is the which is a correlation coefficient, which is in negative form. So we define how we can find the regression line and also the correlation coefficient. Throughout this chapter, we will be doing these things, and we will be predicting some values based on the information that we have and from our linear regression line. So last time we discussed the example one, and there were few examples were left. Before this, I'm going to discuss a little bit things about the limitations. There are few limitations for this process. One thing is causation and correlation. Last time we discussed that what is causation means. Causation means, for instance, one variable is dependent on the other. For instance, if I say that I want to find the crime rate in in a one county, for instance, Ingham County, I'm looking for that what is the crime rate over there and how many population are existing in that, what is the amount of population, how it has been increasing over the last 10 years. So how the population change is going to affect on the crime rate. So that is a kind of two variables. Like on our X, we can say that we have independent variable that we can take, in this case, the population increase increment, and on y-axis we can say that we have a crime rate. So there are two things we can have. One is cause, another is effect. The variable that is basically the cause for making a change in another variable, so that will be on X, so that is our cause. And what is going to affect, that is my Y variable that we will be representing in our Y-axis. So one thing is that, for instance, if we are looking for the relation between two variables X and Y, for sure we can have some mathematical expressions, that is our correlation, which we are representing in the form of R. We are symbolizing Pearson correlation coefficient, which is represented with R. And we have seen that um, if it is less than, if it is greater than equal to 0.75, or R is less than equal to minus 0.75, then it is a good fit for the two variables. So that is telling us that we can have some mathematical expression to represent that two variables are correlated to each other. But for instance, if we have our Pearson coefficient correlation coefficient which is greater than equal to 0.75, that means it is a good fit. But that doesn't tell you that basically X is the reason for making a change in Y. I can give you one of the example, because causation and correlation are not equal to each other. They are not same. The reason is because correlation is just a mathematical expression that tells you, it's a mathematical unit that tells you that how much these two variables are related to each other. But if we have a strong correlation coefficient which is greater or equal to 0.75, that doesn't mean that we can have that X is actually the cause of, this is the cause of making a change in Y variable. Because, for instance, if we have a county, people are living there, and we want to find the crime rate that is increasing over the, let's say, last 5 or 10 years, and we find the number of church in that county. So number of church, let's say these are increasing, axis the number of church in that county. So if X is increasing, Y is increasing, crime rate is increasing, that doesn't mean that if because church is that the amount of church is increasing, this is why murder rate is increasing. No, this is not. So it is not obvious. There might be some other effects that we do not know. For instance, there could have some liquor shops. There could have some shops that can that are selling arms. So these things can be involved, but not necessarily X is a variable or number of churches in that county which is the reason for increasing rate of murders or crime in that county. So causation and correlation, these are two entirely different things. They are not related to each other. But if causation is strong, for instance, we can say, okay, the number of population is increasing in that county. This is the cause for increasing rate of crime in that county. So it can affect, because this is the effect for making a change in the variable Y. This is the number of people, or the number of increasing number of people in that county is basically, it could be the reason for having a crime rate in that county. But that it so for instance, so inversely this is true, that if this is the cause, then it will be correlated to each other. But correlation doesn't necessarily means that it can have a causation. Causation comes from cause. That cause, it means this is the reason, X is the reason for making a change in Y, so this is called causation. But if X is really the cause for making a change in Y, then for sure that X is correlated to each other. But inversely, this is not true for this thing. Hope it will make sense now with the number of counties and with the number of churches and number of population in that county. So it's a little bit tricky in here over here. But one thing I could tell you that correlation and causations are two entirely different things. Correlation is just a variable that tells you mathematically that how X and Y are related to each other, that we described with the unit with the letter R. But causation is something that X is a cause to make a change of a variable in Y. This is called causation. So this is what all it says, that I have described in the form that X is the cause of Y, or it could be the reason Y is the cause of X. So it could be vice versa. Or for instance, like number of churches does not affect the crime rate in that county. So Z, so that doesn't mean, so it we might have another variable that is basically the cause for making a change in X and Y. So it doesn't necessarily that X has to be the cause for making a change in a variable Y. It could be there could be another variable that we are representing with Z that is basically the reason for making a change in both variables. But X and Y are not dependent on each other. Or it could be the reason there are many others, like multiple if you remember that we were discussing in earlier in this chapter, that we can have multiple linear regression, that there could be lots of factors for making a change in a variable y. So that is our multiple linear regression. This is what we are representing in many variables. There are many other factors that can actually the reason for making a change in a variable y. Or sometimes we don't know that how they are related to each other. So these things actually tells you that what is basically the causation, and correlation is just the mathematical unit or mathematical expression that tells you that how these two variables or more than two variables are related to each other. So sometimes we use some common sense, like I gave you an example for the number of churches or the number of crime rate. So for sure, it is common sense the number of churches or number of mosques in any county does not increase the rate of a crime. This is not actually the cause for a crime rate in that county. So this is our common sense, but it could be other factors. Sometimes we can judge things by looking at our data, that this cannot be the cause for the change in variable y. Like for instance, our BMI, which is actually the ratio of height and weight. So BMI does not depend on other factors, that where you are living, what is your age, or where you are living. So it can affect on your diet. It can be related to your diet, what you are taking, but it does not affect it cannot be affected on your age, at what age you are having. So this is the sort of thing that you can make some common sense. You can use your common sense to figure it out, that how these two variables can be related to each other. So this is what it says. Another thing we can see about extrapolation. Extrapolation is predicting outside of known bounds. For instance, in our example number one, we have Brody scorecard points and the murder rate in in some state. So how we can do that? What kind of data we are having? The minimum number of value for X. What is our range of values for what data we are having in our chart? So in our flow chart, or in this raw data, the minimum value for X starts from -28, and the maximum value of X is 56. So this is our bound for X values. So it means if we want to predict something outside of this bound, like if I want to estimate the value of minus, let's say 50, so I cannot predict it accurately. Once I am having a linear regression line for this example, then that least square equation, or that regression line cannot tell you, or cannot be good to find or to predict the value for Brody's scorecard points for -50, because -50 we do not have enough data for making a prediction for the value of -50, because -50 is outside of this bound, because our X values are starting from -28 and all the values up to 56. So this is my bound for the X values we are having. Like in this range, we have this sort of data, that what are the values of Y. But outside of this bound, if any value I want to predict outside of bound, let's say I want to predict something X equals to 70, then I cannot, because because this information or this data is not enough to predict any value for outside of, for beyond the value of 56. So I cannot predict accurately for X equals to 70 in this data. So this is called extrapolation. So what is extrapolation? Says that extrapolation is predicting outside of known bounds. If you have X values on your X-axis, you will look at your minimum data minimum value for x and maximum value of x, for which you have the number of points you are having, or number of data you are, or the data values you are having in your flow chart. So that is my bounded values. What is the minimum value of x and what is the maximum value of x? For instance, in this case, let's say x, we have like x and y, two variables we are discussing, which is simple linear regression. Only two variables we can discuss about, which is x and y. X is the cause of making a change in y, and x is, let's say in this example, x is from 23 to 68. But if I want to predict something outside of this bound, like let's say x equals to 5, then it is not a good fit for our regression line. It cannot predict something accurately for x equals to 5, because we do not have enough values to predict something outside of this bound. And or we cannot use x equals to 72. The reason is because 72 is outside of this bound. So this is called extrapolation. So here is, for instance, and I already explained this to you, that where should we not predict due to extrapolation in the gun loss example, like I have already explained in this example, which is in this one, like it starts from -28 and the maximum value we are having for 56. So this is any value outside for this x values is not my is not actually the best fit. It cannot give you the good estimation for any x value outside of this bound. So this is called extrapolation. And the predictive range is like, it's a range of predictions can vary by a problem, and we predict murder rate when Brady points were 3. So for instance, in our previous example, which is gun laws, in example 1 for the gun laws, we predicted the value of we predicted the murder rate for the Brady points of 3. But you have seen in that data that 3 is actually outside, um, sorry, so this is 3. So 3 is actually the, in the given data we are having for 3 Brady points, we have the murder rate 6.2. But if you remember, by using the regression line, we were estimating the value of y, which was about 4.86. I don't remember exactly. Yeah, this one. So y was, so what was the, this was our regression line for example 1. So when we substitute the value of x, Brady points x equals to 3, so we calculated the value of y, which was 4.86. But if you see your data, from your data for x equals to 3, you have 6.2. So that means why it is different from each other. The reason is, let me explain you in other way. For instance, from our data, given data, we made a scatter plot. So scatter plot gives us the values that is defined in your raw data, like x value and y value. For instance, this is Brady points on your x-axis, and y is your crime rate or murder rate. So for instance, this is my predictive values of all the given values. But if we make a regression line, so which is y equals to ax plus b. So if you draw that line, so it could be like this. So we estimated the value of, let's say, for x equals to 3 here. So so this is, so the value we predicted in our previous example by using the equation we use for, you can see your last lecture, that y is equal to something like this, 0.07x plus 4.65. So this is giving me this predictive line. This is my line. So when I want to calculate the value of x, then I will look at the value of on the line. So this is my predictive value, but actual value was something different in your raw data. So this means that prediction could be different. So why we are saying these things? The reason is that your predictive range could be different. It can be vary by your problem. So so the reason is because there is the vertical distance from the actual point and the point on the line. So that is our distance, and least square values actually reduce some of all the distances of all those values from the of your from your predictive line and all the actual points, and it reduce the this it takes the smallest possible distance of all values for for that predictive line, which is regression line we make. So the predictive value for sure will be sometimes will be different than your actual value of 3. The reason is because our correlation coefficient is not exactly equal to 1. If our correlation coefficient exactly equal to 1, then we can say that our predictive value and our actual value from the data is the same, because your predictive line and all the scatter points are on the line. This is why r equals to 1. But in our case, r was different. R was like in the murder case, we have in example 1, which was r 0.7723. This means our accuracy is not that much. It is little bit, the actual values and the predictive line are little bit different from the actual values. We are taking the nearest possible distance from the actual points, which is our scatter points, and the predictive line. So again, I can explain you that just to be give you an idea that what it is all about. When you have a raw data, so that we can explain it, we can make it in our scatter plots, and y equals to ax plus b, which is our regression line, is the smallest possible distance. It is the line which takes the smallest possible distance from all those values. So this is called the regression line. This is why we have a little bit difference from the actual value and the predictive line. This line is the predictive line, that we make predictions by using this line, that what could be the value of something, of for some value of x. Similarly, you can do that. You can figure it out, the confidence intervals for these predictions, which is not included in this chapter, but when you can review it on your own by in your from your book and from the literature, but that is not included in this chapter. So I just gave you an idea that what it is all about. So what we are going to do, we are going to have a raw data. From that raw data, we will find the regression line, which can give you the best estimated values for all the points on your for all values of x. It can, you can find it, figure it out that what could be the best value, or what could be the best prediction for any value of x on the predictive line or the regression line. So this is called, this is our second example for money and placement. What it does that we want to see if there is a correlation between the money spent on a college wrestling program and their final placement in 2017. So they spent some money on the college wrestling program, and they want to see the relation between the money spent on their colleges and their placement in 2017. So here we collect the data on Big Ten programs. So we collect the placement in the NCAA wrestling finals, along with their expenses on the wrestling teams, which is this one. So we have the wrestling institutions from the following states, which is from Indiana, Michigan State, Northwestern, Ohio State, Pennsylvania State, and all of these. So X is our expenses on the college's wrestling program, for the wrestling program. And Y is our placement programs for these colleges in 2017. So for instance, in Indiana, they spent over $1 million, little over $1 million, $1 million, and Michigan State, a little bit under under $1 million, and Northwestern, they spend some money, and this is our this is, these are all my independent variable X, and Y is their placement programs in 2017, that how many placements they achieved by spending this money in 2017. So what you have to do, that you have to find the least squares regression lines. That means you have to find the value, you have to find the equation for y equals to ax plus b by using your calculator. Find the correlation coefficient, which is r, you have to figure it out. And by seeing the value of r, and I told you how it can be a good fit and bad fit, you have to determine whether this line is the good fit or it is the bad fit. So once it is, then we can predict, once we have all these information, then we have to predict these values for, we have to predict the value of the placements for the following expenses for these programs. So what you have to do, from on your calculator, you have to go to stat, press edit, and then you have list one and list two. On your list one, you will be writing down all the values of X, and I have already written. I have already entered all the values of X on L1, and on L2, I have the value of all the placement for the colleges. So this is what you have to do. Once you enter all of these values, I have already entered list one as X and list two as Y. So once you do that, go to stat, go to calc, and then go to the regression line, the linear regression. Once you press this, you already can see L1, L2, which L1 is your X and L2 is your Y, and then you have to press calculate. Once you press calculate, you will see this y is equal to ax plus b. A is the slope and b is your y-intercept. And you have the value for a and b over here already. And we are not looking for r square. We are interested in r, which is my correlation coefficient. So in this case, from my calculator, the linear regression line, least square regression line, is y equals to minus 2.6635 x. Sorry, it is in scientific notation, so I'm placing it into two decimal places. 266, sorry. This is 266 times 10 raised to power minus 5 x plus b, which is 61.87. This is my least square regression line. And the correlation coefficient R is minus 0.707. So this means R is not a good fit. Why? Because it is greater than minus 0.75. If it is less than or equal to minus 0.75, then it is a good fit. So this is a bad fit. Normally, if it is a bad fit, then we should not predict anything for those predictive line, because it is not a good fit and it cannot give you the best estimated value for y. But in your question, if it is mentioned that, okay, that if you estimate what could be the expected value, or what would you expect a college to place if a college spent this amount of money on their team, then, but if it is mentioned, then go ahead and do it. That how you can do it, this is your x value, place this, put this x value in your least square regression line. So what you will do, that y equals to minus 2.66 times 10 raised to power minus 5, and x is 1,5 1500 in 1000 and plus B value, which is 61.87. So my calculator is giving an error because I don't know, it doesn't accept negative values, but there is some error. But what you have to do, either you can write it in this form on your calculator, that y equals to minus 0.000266 times 15. Either you can write in scientific notation or you can write it in this form, plus 61.87, and then you have to calculate the value what it is. And similarly you have to calculate the value for the following. This one, just you have to do that for your x value is 2 2 million. You have to substitute this value in your equation. On x you will use the value of 2000 thousands, so 2 million you have to substitute, and then you have to figure it out what is the value of y. So this will tell you that what is the value of your placement, the college, the placement in the college. So the next one is that you have to, based on the information, circles all those values where you should not predict due to extrapolation. Extrapolation means that is out of the bounds for the x values. For instance, in this example, we have, if we look at our x values, then the minimum value for x is for Michigan State, which is 973,026, and maximum value we can have a little over 22 million, this one. So, or this one, sorry, this is a maximum value. So any value outside of this bound, like less than this value and greater than this value, will be our extrapolated value. So based on this information, 400,000 is my extra is the value of, is the extrapolation where we should not predict the value of placement because it is outside of the bound. This is also the values where we should not predict, and this one and this one, because our maximum value is not this one, which is, this is not, but these are my values of the extrapolation. 1 2 4 0. So this is included. So this is how we will be you just need to mention all those value which is extrapolated, well, that is outside of the bounds for the x. So these are my extrapolated values. In the next example, money and points, we want to see if there is a correlation between the money spent on college wrestling program and their final points earned in 2017. So now we have the same data, but instead of placement, we are looking for their final scores they earned in 2017. So Y value is the final scores they earned, final points they earned. So we collect the data for these, for Big Ten programs. So for the points scored in the NCAA wrestling finals and the total expenses on the wrestling teams, these are displayed over here. So X values are the same. What you have to do, you only have to change, only have to change the values of Y in your list. So go to edit, because X values are the same, Y values will be different. So I'm going to change the values of Y. So have this is how I have changed all the values for values of y. The x values are the same. So once you do that, go to stat, go to calc, and then go for linear regression. Then press calculate. So now I have this information. So least square regression line y equals to ax plus b. So a is 8.41 times 10 raised to power minus 5. X plus b, which is my x-intercept, which is minus 84.53. The correlation coefficient in this case, which is 0.87 in up to 2 decimal places. So this is greater than 0.75. So this means it is a good fit. So now it is a good fit. So we have to predict the values, like how many points would you expect a college to place if a college spent this amount of money. So what you have to do on your regression line, y equals to 8.41 times 10 raised to power minus 5. X is 1500000 minus 84.53. So now you have to, what I have done only at the value of x, I just place this value that is given. So what you have to do, this is giving me an error. I don't know why. So So this is giving me 41.62. This is my value. Similarly, you can find the value of the points, that how many points would you expect a college to place if your college spent this amount of money. So what you have to do, this amount of money you have to place, you have to substitute in your equation of linear regression line, which is 8.41 times 10 raised to power minus 5. And then at the value of x, you have to substitute, which is 2 million, and then minus 84.53. And then you have to calculate this value on your calculator. In the next example, the Big Mac and happiness, the information we are having, what we have to do, we want to see if there is a correlation between a country's Big Mac index and their overall level of happiness. So that data we collected was collected for a sample of 11 countries. So the happiness, the level of happiness they measured by the Cantrell ladder, that is going to, they are going to call it as a Y variable. So ask those to evaluate the quality of life they're having from on the scale from 0 to 10. Like 10 is the most happiest person and 0 is who are not happy. So Big Mac index is a kind of level which gives you actually that how much amount of money or in terms of dollars you can take in these countries to buy a Big Mac. Like in Australia, you have to take 4.33 US dollars to buy a Big Mac in that country. So this is the value of Big Mac. So these are all the X values, and the and their level of happiness is measured by Cantrell ladder. So we are going to see their relations, at how they are correlated to each other. So you have to find their linear, again, you have to find the least square regression line, the correlation coefficient, and then you have to figure it out whether it's a good fit or a bad fit. So in this case, what you have to do, X at the value, all the values of X will go on your list one, and all the values of Y, for Cantrell ladder, will go on your list L2. So I'm going to go press stat, press edit, go to stat, press edit on L1, where we have for previously we had the dollars and the other values. So, and the placement. So here we are having a data for the X values. The X values for list one is the Big Mac index, and L2 is our Y values for Cantrell ladder. So L1, 4.33. You have to be careful because the order has to be the same, like 4.333 in your L2 has to be 7.272 has to be right in front of 4.33, because these are paired data values. For 4.33 Big Mac index, they have the happiness level measured by the Cantrell ladder, which is 7.272. So this is X and Y values are, this has to be adjacent to each other. So 4.33, 5.25, 3.79. I would recommend you to pause the video and do it on your own, and later come back, and then you can match your values with the following answers. All right. So now I have entered all the values of X and Y. X is L in L1 and X2 is Y, all the values of Y in L2. So you can see 4.33 right in front of my 7.272, because these are all paired points. It has to be accurately this way. Then again, go to stat, go to calc, and then um, stat, go to calc, and then go to linear regression. 4 you have to press, and your X list is L1 and Y list is L2, and the rest has to be empty. And then you have to calculate the value. So this is my least squares regression line. So this is the data you can see on your calculator, least square regression line. So this is Y equals to up to 2 decimal places or 4 decimal places, 0.4080. X plus B is, which is 5.058. So this is the line, the least square regression line, and the correlation coefficient is R equals to 0.78 up to 2 decimal places. Or 4 decimal places, it is 0.7790. If you are writing in 4 decimal places, so this is your value, which is 0.7790. So I am writing the value of R up to 4 decimal places. So this is how I have round off the value. So now it is greater than 0.75, or even if it is 0.75, then it is a good fit. So this is my good fit prediction, the linear regression. Now what we have to do, use this line to predict the happiness level or the Cantrell ladder level. You have to figure it out if the Big Mac index is 3.06. So on your equation of line, which is, we have predicted least square regression line, which is 0.4080 x plus b, which is 5.058. So in this equation, x is my Big Mac and y is my happiness level. So this is, I have to substitute the value of x, 0.4080, x is 3.06 plus 5.058. So now I am going to calculate these values. 0.408. So this is 6.31 up to 2 decimal places. So this is my happiness level. If my Big Mac index is 3.06, then we have happiness level, which is 6.31. This is what we are predicting by using the least square regression line. So in the next example, we have the following data that we want to see if there is a correlation between the number of McDonald's restaurants per million people in a country and their overall level of happiness. And level of happiness, they are measuring with Cantrell level. So this is the data they are having for 11 different countries. So the McDonald's per million, like the number of restaurants or number of sorry, this is opening in the wrong way. So what they are having here, that how many number of McDonald's they are having for in a country per million people, like 30, the number of McDonald's they are having in Australia for 11 different countries, they have the data. In Australia, they have 32.2 McDonald's restaurants per million people. And with this number of McDonald's, the people happiness level in Australia is 7.272. In Canada, they have number of restaurants 33.9 per million people. And their Cantrell level or the happiness level they are having, which is 7.328. Remember, the happiness level is going from 0 to 10. 10 is the most happiest one. So Czech Republic has 5.9 McDonald's per million people, and they have Cantrell level, which is 6.711, and so on, all the values they have mentioned over here. What you have to do, you have to find the least squares regression line for the relation between the happiness level and the number of restaurants they are having per million people, and find their correlation coefficient. And based on the value for, or based on the information for the correlation coefficient, you have to find out whether it's a good fit or a bad fit. So let's do that. All the values of x will go on your list 1, and the values of y will go on your list 2. So go to, first you have to press stat again, stat, go to edit, and then L1 and L2, you have to change all these values. L1 will be your x values and L2 will be your y values. So x is 32.2. You can pause this video and you can do it on your own and check your answers later on. I have entered all the values of x and y in it. X is the number of McDonald's per million, and y is all the values adjacent to each other, where as we are having in the information in the raw data. So then you have to again press stat, go to calc, and then press linear regression on your cal, then press it, and then on your X list is your L1 and Y list will be your L2, and then you have to press calculate. So what is it is giving me, the least square regression line is y equals to ax plus b, and a is the value is given to you, b value is given to you, a is your slope, and b is your y-intercept. So a is 0.01124, x plus b value is 6.6607. Correlation coefficient is 0.2164 up to 2 decimal places. So from the value of R, you can see it's a very bad fit because number of McDonald's cannot affect on the happiness level for the people. So though most of the people are very happy for having McDonald's nearby, but it doesn't necessarily true for when you go for the entire population. So this is a bad fit because this value is less than 0.75 and greater than minus 0.75. So this is my bad fit. Though it's a bad fit, but still we want to predict the value of happiness level. If we have the number of McDonald's per million people is 18.4 for this information. So even if it's a bad fit, I have a linear regression line for the given data. So what I have to do, I am writing it down, the value, the equation of a line, which is 0.01124 x plus b, which is 6.6607. So if my number of McDonald's, which is x, I'm going to substitute this value, 0.01124, x is 18.4, and plus 6.6607. And then you have to calculate the values. So the level of happiness is 6.87 up to 2 decimal places. So this is my predictive value. So there is a little bit way to cheat in this case. What you have to do that if I want to show how we can paint a narrative, like I can change the narrative if we selectively ignore some data that we do not like, or we can selectively focus on data that we do like in the given information. So, and we can also focus on some subsets of the given data from the number of McDonald's examples. In the next two examples, you can see what does it mean actually that, for instance, in this case, this is the following data we are having. I'm not going to ask you to plot it on your calculator, but let me do it for you in this case. Let me see 1 second. And then, so if I'm plotting it on my calculator, so this will be the scatter plot we can have. But in this data, in this plot, I can, if I want to predict something based on I want to selectively choose some of the values from the given data, then I can predict something accurately. For instance, you can see there is no particularly pattern of a line over there, because some points you can see it is your it is above, some points are below, so it's not accurately making a line. But what if I focus on this 4 points, 5 points, 1, 2, 3, 4, like these 5 points, if I figure on, and if I neglect the upper points and all the lower points, if I neglect, then I can make some predictive accurate line for these 5 points, right? So if I will make a predictive line, that it can give me a good accuracy for the results of happiness based on the information. Like you can make you can if you want to, if you selectively choose some points that you like in your given data, then you can make some accurate line in that. So this is what you can do. It's a little bit cheat, you can do that. But for the long term, if you want to predict something for an overall population, then this is not a good choice to do that. Because if you want to estimate for the entire population and you want to check its accuracy, then you have to consider overall the data that you are having, or the best sample you can have to predict some values. But if you are selectively choosing some points, then it cannot give you the best fit, or like you the best fit for the overall population. It will be good for like all the 4 points that I mentioned here. It is good point for the sample, for one sample that I choose, but it is not good for all of those points, because there is no particular pattern you can see in your calculator or in your figure. So what does it mean? For instance, number of McDonald's from the previous example, if I choose these 4 countries, Japan, Norway, Switzerland, and United Kingdom. So what it does, like X values, I'm having 28.4, 11.7, 15.6, 17.8. So if I choose this value for X and their corresponding values of Y, which is the happiness level, then then it can, for sure, it can give you the best accuracy, but only for 4 countries. But it is not good estimation for overall countries that you want to choose for. So for instance, if you are selecting on your L1, so based on this information, only 4 countries out of 11 countries I'm choosing that I like. So what it does, go to your stat, press edit, and then on L1, write down all the values that you're having for Japan, Norway, Switzerland, and United Kingdom. What it does, 28.4, 11.7, 15.6, 17.8. Only these 4 values, and the rest you will delete. And Y value is 5.915, 7.594, 7.487, 6.8. The rest I will delete. So this is my, I'm only from previous example. Now from 11 countries, out of 11 countries, I'm choosing only 4 countries that I want, that I like the most, that can give me the best estimation values as per my need. So if I select these values, this is a little bit cheat. If you're cheating, then you can, you know that you cannot get the accurate answers for the entire population. Again, press stat, go to calc, go to linear regression, X list is L1, Y list is L2, and then calculate. It gave you, you can see, these are the results. Like R value is very accurate, minus 0.971, like nearly, which is very near to -1. So the reason is because you choose some points that can give you the best accurate line for the, that I showed you in the previous scatter plot, that if you choose the points that can make the best line, if you join them together, the best estimated line that can make for you, that it can, then it can give you the best predictive value. So for in this case, for these 4 values, I have the equation, which is minus 0.105, sorry, this is 5, x plus p, which is 8.883. And correlation coefficient is minus 0.9710. So this means R is the good fit. It's very near to -1. It's very accurate. So if you use for only this data, choose the selected number of points over the overall from out of 11 countries, then what will be the happiness level for if you have McDonald's? Number of McDonald's per million is 18.4. So what you have to do in the previous equation, substitute the value of x minus 1.105. X is 18.4 plus 8.883. Then what it will give you? So this is giving me 6.951. So this is my happiness level if my value of x, which is 18.4 in this case. So this is for the selected number of data. Or the next question is asking you, um, the only point is I explained this thing because if you select the number of points that you like from your data, then as you can see previously, it was the correlation coefficient was 0.2164, which was very bad fit, which was not nearly, which was way far from 0.75 if you select overall countries, like from overall population for 11 countries. But if you select only 4 countries that you like, then it is giving you the accurate fit, the best fit line. The R is very near to -1. So it means your calculation is something going fishy. It cannot be the best fit for, or it cannot be accurately giving you information. This sample is not accurate enough for the entire population. This is just a good enough for a selected number of countries, but it is not good for the entire population. So circle in this question, the next question asks you that circle all values where you should not predict due to extrapolation. So in this example, so you can see your least value is in example 6, your least value is 11.7 and the maximum value you're having, which is 28.4. So any value which is less than 11.75 and greater than 28.4 um, is not the good fit, is not a perfect fit for, is not the, you should not predict the value for those values of x. So 0, 5, 10, 30, 35, and 40. So these are not the good fit. So these are the values, these are my extrapolated values where you should not predict the values for y. In example 7, again, we selected few countries from 11 countries from example 7. So you have to place it on your L1 and L2, you have to place it as your all values of y, and you have to find the values on the least regression line equation, regression line for this equation. So I'm leaving it on you. You can do that. And you have to predict the values of y. So I want you to pause the video and then later come back and check all your answers. So my value of the formula for the regression line I'm having on my calculator, which is y is equal to ax plus b, is again slope of a line and B is the y-intercept. So A is 0.0265 up to 4 decimal places, X plus B, which is 6.408081 up to 4 decimal places. And the correlation coefficient is R is equal to 0.9937. So you see that if you select like the selected number of data that you like that can make accurate line from your example, then it can give you the best fit, the very accurate fit at your level that you are what you are looking for. So in this case, R is, which is very near to 1. So this means R is good fit or perfect fit. So using this line, you have to predict the values of predict the value of happiness level for McDonald's per million, which is 18.4. So y equals to 0.0265, x is 18.4, and y is 6.4081. This is my level of happiness if your number of McDonald's is 18.4 in the following data points. The predict in this example, if you predict, then this is your level of happiness is, which is 6.8957. Again, from the following data, in example 7, you have to circle all those all the extrapolated values, which is outside of the range of values of X. So in this example, the least value is 1.8 and maximum value is 33.9. So any value which is less than 1.8 and greater than 33.9 is your extrapolated value. So this is this one, this one, and this one. This is my extrapolated value, 33.9. So that's it. So, so here is the key, or here's the crux of this topic, that because we want to, the overall idea for statistics is that we want to predict something for the entire population, right? And if you want to predict something that is the good fit or the best fit, you want to make some model for the best as estimated value for the population, then in order to do that, we have to get some good samples that can actually reflect the values of the population. In examples, from these examples, like in example 5, you have seen that we have 11 different countries we had the data for, where we have the number of McDonald's per million people, and then we have their happiness level. But for sure, some people are happy to have McDonald's near, but it does not really mean that people happiness is actually based on the number of McDonald's they are having in their countries. But if we, and this is the reason that in example 5, we have the correlation coefficient was really bad, which was 0.22 something, which was very bad. So this is why that was a bad fit. But if we had selected some samples that can give me the best accurate ideas, like in your in example 7 and in example 6, when we selected 4 countries, and that can giving me the best estimation line, which was nearly very good fit um, for that data, like 4 different countries. But my examples, these samples of example 7 and example 6 is not reflecting actually my bigger data, which is for 11 different countries. So if I have 11 countries, 11 countries, for instance, if we have overall like 32 or like more than 32 countries in overall population we are looking for, then 11 different countries is nearly a best sample, or it's a good sample to estimate the values of the entire world, or the entire population. But this is the selected values for X, or the selected model which we choose in our case, that can tell me where I knew that this can give me the best fit for my predictive line or the linear regression line. So this model is not a good model. Like example 6 and example 7 is not a good model to predict something for the entire population for overall countries. So example 6 and example 7 is not a good model to get a best estimated values for the entire population, or for all over the countries in the world, for their happiness level, based on the McDonald's they are having in their countries. So this is why we have to be very careful in selecting the samples that what we are choosing, because the selection of sample is actually reflecting your results for the entire population. So this is why if you randomly picked some values, then you have to be very careful. You need to have some accurate guess that how it could be the best fit model that you can make. So this is why the statistics have the beat anecdotes. So this is what happens in statistics, that like in our this examples, statistics is based on overall like guess. You can see there are some beat anecdotes that you have to that come up with in your samples, in your all examples. Like in my example 6 and 7, like this is the reason that we do testing for a lot of different things. We do not make some predictions only on few examples or only on few samples that we are having. This is why in statistics we do lot of testings, and we do experiments on lot of samples, on lot of examples. So then we analyze all those results to make some best predictions about our future outcomes. So this is why this happens in statistics, that all of your conclusion based on your testing results on your samples that you are having. Like this happens overall in, because now this is the world of AI, artificial intelligence. We have robotics, we have, you know, in your, even in your emails, you can see that that when you write something, there is actually they give you the answers that you want to write. For instance, how are you, and if you're writing that I am okay or I am fine, like all of these things, when you write down, it already give you all of your answers. Similarly, when you do shopping on Amazon, when you select something, then it give you some all of the choices side by side, that okay, so because this, where, how do computer know, how do they know that this is what you are looking for? So these all happened because of the samples they choose. They have all the experiments they are having, that they check the behavior of the people, that if they buy this, that they can buy these things. Like for instance, if they buy the for instance, if they buy um, let's say a calculator, that for them for sure they are looking for some cells. So this is how they check the behavior. So this is all statistics basically. AI is all statistics, and statistics is the backbone for the artificial intelligence nowadays. So that's it. This is what I wanted to let you know. And we have finished our course. In the next week, I will do the practice test for the finals. And also, I want you to show a little bit of programming, like how people use statistics in industries, how they have some projects and how they do analyze things by using the statistics, that we have studied so far. I want you to get the taste of this subject by using some coding, and I want you to analyze things, that how we can analyze things in the practical life. If we have some data, how we can read it, how we can find their mean, mod, median, or like how we can shape this in, or make a graph, and how we can do the analysis practically in a real world problems. So I think this will be a very exciting for you. If you um, like if you will get this taste, then I hope that you will like this subject. So next week we will do it, and thank you so much. Don't forget that chapter 9 um, test is due. So next week, hopefully that chapter 10 and chapter 12 quiz, I will do it all together, and that will be due next week. So thank you so much. Have a great weekend.